Hello friends, and welcome you again in yet another lecture on digital communication. In previous lecture we have discussed about the transmitter and receiver block diagram of PCM system. Now in this lecture we are going to see about the process of quantization, what it means, and how the signal to quantization noise ratio will be decided in PCM. First, we will look for the quantization process. So, as said earlier, the process of quantization is nothing but approximation or rounding off of each and individual sample level to the predefined nearest level. This quantizer will definitely convert the sampled signal into the approximated quantized signal by taking the finite number of quantized levels into consideration. So let's see that here the signal which is represented by red color is our original signal, that is input signal x of t. While on this x of t, if you are observing here, we have given the different markings with blue lines, and from one previous blue line to another previous blue line we have marked that as a delta 1, delta 2 and delta 3. That means these are the range of amplitude levels which will be rounded to the nearest predefined value. In between these dark blue colored, we are seeing another dotted lines, and those dotted lines are nothing but the quantization levels, or they are also said to be the thresholding levels, and they are nothing but the predefined levels where these range of values are going to be rounded off. In short, what we can see is if the signal is going to change in the range of this delta 0, that is from this reference line up to first blue color line, it will be going to be quantized or going to be rounded off to the nearest quantized level of Q0. Similarly, if the signal is in the range of delta 1 values, then it will be rounded off to the Q1 value, and so on for the next coming original signal levels, and predefined quantized level mapping will happen. When we are changing from one particular quantized level to the next quantized level, this vertical distance between the two consecutive quantization levels is said to be the step size, which is marked here on vertical axis as S. So in quantization, how to get now these predefined levels and the range of values? So to consider that number of predefined levels, we have to go for finding out first the lowest and highest excursion of the given signal. Let's see, in this given signal, this highest peak what we are going to obtain is marked as a VH, and this lowest peak what we are going to obtain is marked as VH. So this signal is going to excurse in between the levels of VL to VH. In the next part, we are finding the step size, that is the vertical change of the signal, as VH minus VL divided by Q, where this Q is nothing but the total number of divisions for the given range of signal. If suppose I am having Q is equal to 8, then it will give me the step size as VH minus VL divided by 8. For this Q equal to 8 itself, we are finding the levels which have been defined as a predefined quantization levels, which have been marked from this Q0 to Q7. These levels will be also called as a decision thresholds or quantization level. Now, there is one question, why this quantization process is needed, or what is the usage of this quantization process? So if this process is not used, then each and every individual sample level after the process of sampling has to be mapped to some predefined, indicated or converted into the digital world. And here the number of levels will be more as compared to the number of levels what we are going to get after the quantization process. And if the number of levels are more, the bits which are used for the level encoding will be more in number. Per this per word number of bits increment will also give the effect as increasing requirement for the bandwidth of the channel when data is transferred. So if suppose I am having 256 quantization levels, those are defined, then there will be 256 number of sample values, and that's why to represent these 256 quantization level I will need 8 number of bits per word. In other words, I can say if my ADC is of 8 bit, I can have maximum of 256 number of quantization level presentation. We have said that in quantization the rounding of effect is going to take place, and when the rounding is going to take place, definitely the error is associated with that process. Error which is associated with the quantization process is named as either quantization error or quantization noise, and the symbol for representation is epsilon. Epsilon is mathematically written as the subtraction value of an input signal from instantaneous value of that quantized signal, which is mentioned as xqt minus x. We have said that this quantization level and step size are related with each other, and if we are considering the step size is of total value s, then above the quantization level there will be half of the step size will be present, and below the quantization level half of the step size will be present. Let's look for this diagram once again. This is the quantization level, and for this quantization level the step size has been shown over here. So this step size is present below this original signal level with the half value, and above this signal level with half value. That means the total step size will get divided with the value of s by 2 above and below the original signal level. And because of that, if I am going to find out the difference between the quantized level value and the original signal level value, it will be either plus s by 2 or it will be minus s by 2. So if I have to get the reduction to be done in the quantization error, then I have to get the step size to be decreased. And if step sizes are decreased, then number of quantization levels are going to increase. That means if I have to reduce the quantization error, we have to increase the number of quantization level or number of predefined level. Now we will be moving towards the deduction of equation of SNR for the PCM system, and for that we are starting from the quantization error mean square value, as the step size is with s value, and we have said that quantization error is going to vary from minus s by 2 to plus s by 2. So its mean square value is going to have the label as s square divided by 12, and we have set up the relationship between the quantization levels and the number of bits which are used for representing the levels as q is equal to 2 raised to n, where q stands for number of quantization level and capital N stands for number of bits used per word representation. So if I want the quantization noise should be small, then I have to reduce the step size, and we have to go for increasing the number of quantization level. Now we will move towards the derivation of quantization error. To start with this derivation, again we have to consider one time domain continuous signal whose value is going to vary between the levels of VL and V. So the total variation occurring in the amplitude for the applied signal will be calculated as VH minus VL. Now let us assume that VH is equal to plus V and VL is equal to minus V. Then the total variation in the amplitude will be obtained as 2V by substituting the values of VH and VL as these values. Now if we are dividing this whole variation of a signal in Q number of quantization levels, then we can find the step size as S is equal to twice V divided by Q. Let's say V is equal to 1. So this 2V will reduce S to 2. So S will become equals to 2 divided by Q. So if step size is sufficiently small, then the quantization error can be assumed to be uniformly distributed. And that's why we are saying that quantization error is a random variable having the uniform distribution over the number of frequencies or over the number of signal present. But we have stated that quantization error is having minimum value of minus S by 2 and maximum value of plus S by 2. So we will take the representation of this quantization error as a probability distribution function. So the error is going to change its value from minus S by 2 to plus S by 2, and this function will be uniformly distributed for the changes from minus S by 2 to plus S by 2. So we can say here that this function as a probability density function can be represented as f of epsilon to the base epsilon is having magnitude as a 0 when epsilon value is either greater than S by 2 or it is less than or equal to minus S by 2. And for the region between minus S by 2 to plus S by 2, it will have the magnitude as 1 by S. Now we will go toward getting the mean average value of quantization error. As we are saying that this quantization error is uniformly distributed above the original level and below the original level. If we are taking the average of this quantization error around its original value of the signal, then it will definitely become equal to 0. The noise power is always obtained as V square divided by R, and for the noise signal the V will be replaced by Vn square, so it will be obtained as Vn square divided by R. Now for the quantization noise is also a random variable with the PDF that has been represented in above figure, which was having uniform distribution. Now let's find out the mean square value for that probability density function of quantization noise. Mean square value is represented as expected value of squared resultant of epsilon. So it is nothing but epsilon square. It is mathematically represented as integration from minus infinity to plus infinity epsilon square probability density function for the distribution of this error with respect to small changes in error. But we have said that our error is going to spread over the limits of minus S by 2 to plus S by 2, and during that region only its magnitude will be 1 by S, and at other limits its value will be 0. So this equation of integration will change its limits as instead of minus infinity it will be minus S by 2, and for plus infinity it will be replacing as plus S by 2. At the same time this epsilon square will be kept as it is, but the function value for this probability density function over this range is nothing but 1 by S. So this function representation will be replaced by 1 by S. Now we will calculate the integration for this. If we take the integration, it will be epsilon square as it is kept, then epsilon square divided by 3, 1 by s will be taken outside, and for this epsilon's value we are substituting the limits as s by 2 and minus s by 2. So finally, by doing all the mathematical processes over here, we will get the resultant as s square divided by 12. So we can say that the mean square value of the noise voltage is s square divided by 12. But we know the mean square value will be written as a normalized value if for the r we are substituting as 1. So the noise value for the quantization process is nothing but s square divided by 12. When we are obtaining the expression for maximum signal to quantization noise ratio, it is nothing but the ratio of normalized signal power to the normalized noise power. And just now we have derived the normalized quantization noise power value is s square divided by 12. Now let's go towards getting the normalized signal power, and to obtain that again we are starting with the signal accretion, which is between minus v to plus for this continuously changing analog variable. Now the power dissipated in resistance R by the signal voltage V will be given as RMS voltage square divided by R, and we know that RMS voltage for any continuous time domain signal will be given as amplitude divided by root 2, and its amplitude for the signal is plus v, so it will be v divided by root 2. So signal power calculation will be again v square divided by r. So v value here is actually v by root 2, so that will become as v square divided by 2 r. But the normalized power, if we are going to find out, r will be substituted as 1, so this v square divided by 2r will be reduced as v square divided by 2. So we will now substitute normalized signal power as v square by 2 and normalized quantization noise power as s square divided by 12 in the equation of Sn. This equation will get reduced by some modifications as 6v square divided by s square. But we know that S is equal to 2V divided by Q, where this S is nothing but the step size, V is your maximum excursions for the signal, Q is the number of quantization levels that we have predefined. So in this equation of SNR, we are going to substitute for step size. So in denominator, we will substitute for S as 2V divided by Q. But it is s square, so 2v will turn out as 4v square, and that divide by q square will goes into the numerator. Then this modification we will do, v square will get cancelled, so remaining part will be 3 by 2q square. Now this SNR we have obtained in terms of number of quantization level, but we are interested to find out the value of SNR in terms of number of bits used per word representation, that is in n form. So we are substituting the relationship for q as 2 raised to n, but already it is q square, so it will be 2 raised to 2n for this substitution. So SNR equation will reduce us as p divided by nq is equal to 3 by 2 as it is, and for q we are substituting 2 raised to n, and this 2 as it is in the power will appear, so the power of 2 will be 2 raised to 2n. So this is the maximum SNR value. But now one another thing we want to convert, and that was the thing of SNR conversion in dB. As it is power value itself, so we have to take 10 log for this SNR power value. So we will write 10 log of 3 by 2 into 2 raised to n. So this log will get distributed on the multiplication, so it will be written as 10 log of 3 by 2 plus 10 log of 2 raised to 2n. And when we will get this to be completely solved, we will find out the answer as 1.76 plus 6n. And this is the final SNR equation for PCM system. So from this equation we can state one conclusion, and that conclusion talks about the relationship between the SNR value change with respect to the bit increment into the PCM code word representation. Corresponding to a single n value change, extra 6 dB will be included into the SNR. The final conclusion statement is that the SNR for PCM will be increases by 6 dB for every 1 bit increase in number of bits in PCM code word. Well, students, you might have understood now what is the equation for SNR for PCM and how it has got deduced. So, bye. Until then, you go through these concepts and get the happy